The Webb peers such a long way out that it is receiving light that has been voyaging for more than 13 billion years. Despite this, the universe has grown, and thus the light has been stretching. For the most distant galaxies, we are looking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we refer to as the singularity. Currently, this operates in the manner of interpreting the Big Bang hypothesis. Anyway, the Space Telescope with James Webb, JWST, has revealed significant secrets about the origins and development of the universe. These discoveries leave us confused, and famous physicist Brian Cox has proclaimed that the astonishing discoveries made by the JWST might actually reshape our perception of the entire universe. Join us as we investigate these brand new divine disclosures that promise to upset our understanding. The James Webb Space Telescope, named after the distinguished NASA Administrator James E. Webb, stands as a wonder in current galactic investigation. This telescope symbolizes a huge technological leap forward from its ancestor, the Hubble Space Telescope. Being the result of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its predecessor. It makes use of cutting-edge technology and a layout that is ideal for studying the universe in remarkable detail. Unlike the Hubble, JWST's images are crisp and clear, providing pictures of distant heavenly bodies. Working primarily in the infrared range, this unique feature allows it to cut through cosmic dust and capture objects in space that were previously hidden from view. With its enormous 6.5-meter primary mirror constructed of 18 hexagonal segments, the JWST dwarfs the Hubble's mirror. Situated about 1.5 million kilometers away from Earth at the second Lagrange point, L2, it revolves around the Sun in a state of equilibrium with Earth, ensuring a constant and stable view of the universe. Looking into the distant corners of the universe and exploring light years away also involves a form of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. The light from these objects, due to the expanding universe, undergoes a redshift, moving from the visible spectrum to the infrared range or longer wavelengths. Fortunately, the JWST can detect infrared light emitted by celestial bodies spread far enough apart for scientists to study the birth of stars, investigate the formation of galaxies, and examine exoplanet atmospheres. Its latest notable discovery entails locating an enormous mass of galaxies at the edge of the observable universe. This finding challenges the veracity of the Big Bang theory, prompting us to rethink our central cosmological assumptions. To better understand how we arrived at this point, let's take a brief journey through the history of space exploration. Early civilizations, like the Greeks and Chinese, laid the foundation for comprehending the motion of the planets. Newton's laws, formulated in the 17th century, provided a theoretical framework for space travel. In the early 20th century, Edwin Hubble, an influential astronomer, made historic cosmological discoveries. His observations revealed that distant nebulae were separate galaxies far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, formulated by him, demonstrated that galaxies farther away were moving at higher speeds, proving the expansion of the universe. The post-war era marked the beginning of the space race, with the Soviet Union launching Sputnik in 1957, followed by Yuri Gagarin's orbital flight in 1961 and the Apollo 11 moon landing in 1969, landmark achievements. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and incredible insights into the universe. The transition from early observations to the James Webb Space Telescope highlights the steady development of our understanding of the universe. Hubble's most iconic achievements include capturing the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, which captured thousands of galaxies in what appeared to be an empty patch of space. Hubble also played a role in identifying the atmospheres of exoplanets, detecting elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the closest observed supernova, SN 1987A, it shed light on the life cycle of enormous stars. These achievements established the Hubble Space Telescope's legacy as a foundation of modern space science, captivating the world with its incredible astronomical discoveries. Its successor, the James Webb Space Telescope, was designed to expand upon technological advances and lessons learned from Hubble. One of the primary focuses is our understanding of the universe's origins, which today is explained by the prevailing Big Bang theory. The universe began approximately 13.8 billion years ago as a hot and dense singularity. It rapidly expanded, resulting in the formation of matter, energy, and fundamental forces. As the universe cooled, it allowed for the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the theory faced skepticism and challenges in its early years. Alternative models, such as the steady-state theory, proposed a universe with no predetermined beginning. Concerns arose about the evidence supporting the initial singularity, the expansion mechanism, and observed anomalies. Many of these issues were addressed over time, with a critical piece of evidence coming in 1965, the detection of cosmic microwave background radiation, which aligned with Big Bang predictions. Space missions such as WMAP and advancements in technology further supported the theory. Precise measurements of cosmic microwave background radiation matched theoretical predictions remarkably well. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust clouds. Primarily working in the infrared range, the JWST captures the oldest light in the universe, observing objects that formed shortly after the Big Bang. Its capabilities allow it to focus on star-forming regions, stellar nurseries, and the birth of stars, areas obscured from optical telescopes. Infrared light, with longer wavelengths than visible light, penetrates interstellar dust clouds, overcoming a limitation of the Hubble Space Telescope. The JWST can detect cooler objects emitting primarily infrared light, making it ideal for researching phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light stretches, causing a redshift. The JWST detects these redshifted signals, capturing light from the early universe and offering insights into its development and formation. Exciting events like black hole formations or new star births predominantly emit in the infrared range, expanding the JWST's observational capabilities. The implications of JWST's discoveries. The unexpected abundance of massive galaxies in the early universe has challenged long-standing theories about cosmic evolution. According to traditional cosmological models, galaxies should have taken much longer to grow to such enormous sizes. However, JWST's observations suggest that galaxies formed and evolved at an accelerated pace, far beyond what previous theories predicted. This discrepancy raises fundamental questions. Were our assumptions about the early universe incorrect? Are there missing factors in our understanding of how matter coalesces into galaxies? Could alternative models of cosmology better explain these observations? One possibility is that our understanding of dark matter and dark energy, the invisible forces that govern cosmic expansion, may need revision. These mysterious components make up about 95% of the universe, yet they remain largely theoretical. If our estimates of their behavior were even slightly off, it could significantly impact our predictions about how galaxies formed. Another hypothesis suggests that the laws of physics may have operated differently in the early universe. While this idea is highly controversial, some physicists speculate that fundamental forces, such as gravity, may have functioned differently in the universe's infancy, allowing structures to form more rapidly. Revisiting the Big Bang theory. The JWST's discoveries do not necessarily disprove the Big Bang theory, but they do raise important questions about its details. For decades, the standard model of cosmology, known as the lambda cold dark matter (CDM) model, has provided a reliable framework for understanding the universe's evolution. However, the newfound galaxies suggest that this model might require significant refinements. For example, if galaxies formed much earlier than expected, then the timeline of cosmic evolution might need to be adjusted. This could imply that the first stars ignited sooner, that cosmic inflation behaved differently, or even that undiscovered physical phenomena played a role in shaping the early cosmos. Some alternative theories propose that the Big Bang was not the absolute beginning but rather a transition from a previous cosmic state. The concept of a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction, has gained renewed interest in light of these findings. Could the JWST's data support such a model? The role of the JWST in exploring exoplanets. Beyond studying the distant past, the JWST is also revolutionizing our understanding of exoplanets, planets orbiting stars outside our solar system. By analyzing the atmospheres of these distant worlds, scientists can determine their chemical compositions and assess whether they have conditions suitable for life. The telescope's ability to detect biosignatures, such as water vapor, methane, and carbon dioxide, offers a glimpse into the potential habitability of exoplanets. Some of JWST's most exciting findings so far include TRAPPIST-1 system, a star system with 7 Earth-sized planets, some of which reside in the habitable zone where liquid water could exist. WASP-39b, an exoplanet with detected carbon dioxide in its atmosphere, providing key insights into planetary formation. K2-18b, a super-Earth where JWST detected possible evidence of dimethyl sulfide, DMS, a molecule associated with biological activity on Earth. The prospect of finding alien life, even in microbial form, would be one of the most profound discoveries in human history. While no definitive evidence has been found yet, JWST has taken us closer than ever to answering the age-old question, are we alone in the universe? Unraveling the mysteries of black holes. JWST's infrared capabilities also allow it to peer into the hearts of galaxies, revealing the nature of supermassive black holes. Scientists have long known that nearly every large galaxy hosts a black hole at its center, but JWST has detected some of these cosmic giants in galaxies that formed shockingly early in the universe's history. These discoveries raise intriguing questions. How did such massive black holes form so soon after the Big Bang? Did they grow from smaller black holes merging over time, or did they originate in a more mysterious process? Could black holes have played a role in shaping early galaxies, rather than forming within them? Some researchers speculate that primordial black holes, theoretical objects formed during the earliest moments of the universe, could explain these findings. If such black holes exist, they could provide new insights into dark matter and the fundamental structure of the cosmos. What comes next? As the JWST continues its observations, it is expected to challenge even more aspects of our current cosmological understanding. Upcoming studies will focus on mapping the first galaxies, determining how early structures formed and evolved, investigating dark matter and dark energy, testing theories about their role in shaping the universe, exploring exoplanets in greater detail, searching for more signs of potentially habitable worlds. The telescope's discoveries have sparked lively debates in the scientific community. Some argue that the standard model of cosmology remains intact and only requires minor adjustments, while others believe a paradigm shift may be necessary. Regardless of the outcome, one thing is certain: the James Webb Space Telescope is revolutionizing our understanding of the universe. With every new image and dataset, we move one step closer to answering humanity's biggest questions about our cosmic origins, the nature of reality, and the possibility of life beyond Earth. Suggesting a more complex and rapid development process, some of the earliest observations of galaxies appeared more structured than expected, challenging conventional models that predicted slower evolution. The discovery of an immense mass of galaxies challenges the assumed distribution and arrangement of massive structures, revealing something more complex and dense than previously thought. These cosmic web observations raise interesting concerns and open avenues for further investigation. The existence of such massive structures challenges early models of large-scale structure formation, prompting researchers to refine their models for a better explanation. Understanding how such enormous structures gathered rapidly following the Big Bang presents a puzzle that requires an explanation without violating key principles of cosmology. Significant discrepancies in the early universe's conditions, in contrast to predictions made using traditional models, have led to the development of new theories. These differences may suggest previously unanticipated physical processes, unknown conditions, or unidentified astronomical phenomena. Simply put, these variations have prompted scientists to reconsider and improve our models of the universe. Currently, all we can say is that further investigation is required to incorporate these surprising observations into a more comprehensive understanding of the origins of the universe. Observations often provide exciting glimpses into the cosmos, but in-depth analysis occasionally reveals discrepancies. For example, early observations of distant galaxies may indicate specific features or properties, but closer examination can reveal differences in their formation, structure, or evolutionary pathways. In simple terms, cosmic phenomena are extremely complex and necessitate careful investigation for us to truly understand their actual nature. One method that helps unravel the properties and history of celestial objects is spectroscopy. It involves analyzing the light emitted or absorbed by celestial entities. By examining the properties of light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us comprehend the origins, growth, and contributions of these heavenly bodies to the cosmic tapestry. The James Webb Space Telescope, JWST, has uncovered various instances where initial observations differed from later analysis. For instance, early observations of distant galaxies suggested a composition overwhelmingly dominated by light elements such as helium and hydrogen, aligning with theoretical expectations. However, spectroscopic analysis using JWST revealed intriguing differences in elemental signatures, identifying heavier elements or compounds previously undetected or underestimated in the early universe. These findings challenge conventional ideas about the early universe's chemical makeup and the processes responsible for the formation and distribution of elements across cosmic distances. Moreover, initial assumptions about galaxies in the early universe were based on basic observations suggesting a relatively uniform pattern of evolution and organization. However, broader investigations by JWST have uncovered a much more diverse range of structural configurations within these galaxies. These differences have reshaped our understanding of evolutionary pathways, suggesting that the forces governing the structure and development of galaxies in the early universe may be far more complex than previously thought. On the other hand, JWST has also confirmed some earlier theories and observations. For example, spectroscopic measurements confirmed the presence of oxygen, hydrogen, helium, and nitrogen within celestial objects, supporting theoretical predictions. These findings align with the widely accepted lambda cold dark matter (CDM) model, which suggests that the universe began with the Big Bang and consists of ordinary matter, and dark energy. However, some predictions of this model have been tested by later JWST discoveries, leading to the consideration of alternative possibilities. The cold dark matter model proposes that most of the universe's matter is dark matter, an elusive form of matter that does not interact with light but exerts a gravitational effect. This model aligns with our understanding of cosmic microwave background radiation on a large scale, though challenges arise at smaller scales, particularly regarding the structure and abundance of small satellite galaxies around larger ones. Another alternative is the semi-steady-state cosmology, which suggests the universe follows a repeating pattern of continuous expansion and contraction. However, this model remains speculative due to its deviation from traditional models and the lack of direct observational evidence supporting its cyclical nature. The mirror universe hypothesis suggests the existence of an identical parallel universe running alongside the one we observe. This model indicates that the mirror universe may have its own distinct physical laws and particles, offering an alternative explanation for various cosmic mysteries. However, it lacks observational evidence or test data and remains largely speculative. The digital simulation hypothesis asserts that our universe may be a highly advanced programmatic simulation, akin to a virtual reality. This idea originates from philosophical considerations and encounters difficulties in providing observational confirmation or disproof. Finally, the multiverse hypothesis proposes the existence of multiple universes, each with its own set of physical laws and properties. According to this theory, our universe is just one among an infinite number of universes, each with different constants and possibly even dimensions. While intriguing, this hypothesis remains speculative, as we cannot directly observe or access other universes. While alternative cosmological theories may not be as widely accepted as the CDM model, it is important to remember that even the latter faced skepticism early on. Confirming or disproving these speculations is challenging, but they may warrant consideration if our current cosmological model encounters significant challenges over time. Recent discoveries, though eye-opening, have not disproven the Big Bang theory. According to many experts, observations from the James Webb Space Telescope have enhanced our understanding of cosmic history, aligning with Big Bang predictions. Massive groups of galaxies at the farthest reaches of the observable universe suggest that gravitational forces were at work even in the universe's infancy. The presence of these massive structures at the edge of the observable universe implies that their light has taken billions of years to reach us, offering a glimpse into the universe's past and supporting the theory's predictions about its evolution. However, these observations also present inconsistencies that merit objective scientific scrutiny. JWST has opened up new vistas, allowing us to explore the ancient realms of the universe. We are now confronted with a cosmological landscape full of new questions, fascinating possibilities, and ambiguities that challenge established cosmological principles. These findings prompt a re-evaluation of our understanding of the universe's birth, development, and fundamental laws. In light of such discoveries, it is crucial to remain open to new perspectives on our cosmic narratives.